Are you able to hear me? Okay, then start. Okay. Are you able to see my screen? Okay. Welcome everyone. This is the second live interactive session for the course Artificial Intelligence and the Material Science in oh, Artificial Intelligence and Machine Learning in the Materials Engineering, and which is being instructed by the Professor Krishanu Vishwas, and I'm the Shivam Aggarwal, one of the TA for this course. Uh, in this session, I will discuss all the things which will help you to solve the assignments which are given on the NPTEL portal to solve you guys. So, see what are the materials? Uh, what do we mean when we say materials? When I see around me, or you can also see around you, there are the different kind of things which are placed everywhere. All of these things are the materials. Like I'm using this pen, or I'm using this laptop. It is made of the different kind of the materials like plastic, silicon, and there will be some copper, aluminium, and many things. So when we see the different kind of materials around us, then we can classify these things into the some class in the some classes, like uh, if we see the properties of those materials, and on the properties of those materials, generally materials are classified in the four parts, four classes, like first metals, then ceramics, then polymers, and the composite. Composites are not generally a class of materials, but it is the mixture of it is the homogeneous or the heterogeneous mixture of the two kind of these materials. Maybe the metal plus ceramic, metal plus polymer, ceramic plus metal, ceramic plus polymer. It can be the mixture of the two this class of materials. So when we talk about the metals, there are the some properties associates with the metal, and if any material have those properties, then it is called metals. Like ductility, metal have the ductility, they are shiny, and they are the generally have the very good electrical conductivity, and they are solid in nature generally. But just like everyone, you know, the mercury is a metal, but it is in the liquid state at the room temperature. When we called about the ceramic, they are brittle in nature, and they are generally have the low electrical conductivity, and it is a hard material generally. But when we talk about the polymers, they are like soft, which is like your when you say the polymers like glue, they can be liquid and solid both. And when we talk about the composite, generally composite, I discussed in a start, like the composite are the mixture of any two of things in this group, like metal, ceramic, or polymer. Two or two or three. Okay. So first we will discuss about the metals. What are the what are the metals? Metals are generally have ductility, very good electrical, and some like these properties they have, which we also learn in the high school physics or chemistry. And when we talk about the ceramics, many for the many of the student, maybe this word is a new. Uh, we generally thought about the like metal, semiconductors, and insulators. Generally, both semiconductor and the insulators come in this class. Ceramic. What are the ceramic? It is a generally containing. Sorry. It this material generally containing the some metallic or the semi-metallic or non-metallic elements. Like it is a make of the two or three elements, and they are maybe metals, non-metals, or semi-metals also. Like example, like some carbides, like titanium carbides, borides, oxides also like titanium, TiO2, Al2O3. These all are come in the class of the ceramics. Why? These kind of materials have the some properties. So that like the glass is also a ceramic material. When we talk about the polymers, first we talk about the term mer. If we talk about the polymer, actually mass is a like a unit which is get repeated in talk about the polythene. Uh, that polythene, it is the like a chain of the uh, a organic molecule. And in similar way, polymer is a class of the material which generally repeat the a term, a organic molecule, which we generally call the mer, and it make a very large chain, like an infinite chain. And that's why these kind of material are generally flexible due to having this chain and having the carbon bond in itself. Like there are some example thermoplastic polymers and the thermosetting and thermoplast polymers. There are some other examples like glue, which are generally used uh, to uh, to joint two materials like paper or any solid or things. If we are talking about the composite is generally a mixture of the two or many materials. Like if I talk about these the metals, there is the ceramics, and there is the polymers. If I mix these things, then this is called the metal polymer composite. If I mix metal and ceramic, then it will be called the metal ceramic composite. In similar way, if I mix the polymer and the ceramic, then it is called the polymer ceramic composite. But why we make the composite when we have a different class of type of materials like metal, ceramic, and the polymers? Because sometimes we need like if I talk about the polymer, have a different characteristic. Like it is flexible, it has uh, low service temperature compared to the ceramics, and ceramic are generally hard, and they are in the brittle in nature, and they have generally the low electrical conductivity. But we talk about the metal, they have the high electrical conductivity. So if I need any material which have the some properties like the ceramic and also the metal, so I have to design composite in a such a way that has the both the properties when I mix the ceramic and the metals. There is a plot which sir is also shared. Like here is the electrical resistivity and the thermal conductivity of the different group of the material. Like this is the glasses, this is the polymers, and these are some natural materials like wood, leather, cork, and these are the some ceramics which have the you can see the electrical conductivity range from the 10 power 2 to 10 power 24, and you can see also the thermal conductivity. And by seeing this graph, you can select the material which can be useful for your application in terms of the thermal conductivity and electrical resistivity. If you look for the other property, you have to see those also to select the material. But after this classification of the materials, generally the properties of the material of any material uh, can be like the any from the if I talk about the any material you have, the properties of that material is depend on the several factors. Like first it is talk about when I talk about the its atom, it's a constituent atoms, from which atoms it makes, like it's silicon, it's a carbon, it is a magnesium, what kind of atom it is have. Then how, what the structure they have, about the if I talk about the carbon have the different kind of allotropes. Why? Because it has a different crystal structure. Like if I talk about the graphite, that has a different crystal structure. If I talk about the diamond, that has a different crystal structure. Or in terms of some allotropes which are found recently, like carbon nanotube, that has a different crystal structure. That's why their properties are also different, in spite having the same atom in that. Okay. After that, if I talk about the after the structure, there is a the processing, how they are made. What is the microstructure of those? How the structure is structure is the atomic structure here. This structure. But when I talk about the I have the a material which is in the millimeter size or larger than that, which I can say by the naked eye. So that have the different microstructure. What is the microstructure? Microstructure is the arrangement of the different structure. Mm, you have a material that has the kind of a type of structure. I talk about I will say it has the arrangement for the like this. This line gives me the insight what is the structure of the material. When the a material when we make a material in a larger size, so there are the generally two types of a material: single crystal and the polycrystalline. See, what is the single crystalline? Single crystalline material have the same structure uh, in the all material. I have a quartz crystal, this, so it has the same structure everywhere in that material. That is called the single crystal. If I talk about the dimension, just suppose 1 centimeter. Okay. If I talk about the polycrystalline, if there is a polycrystalline material, then there will be some different type of crystal structure in that, like it can be in this direction, it can be in this, it can be in this. So all of them have the same crystal structure, but their arrangement are changed. Like just they are oriented randomly. And if we see that microstructure, we can see the different kind of images here. Like it is a dark, light brown. There is a lighter, and this is a dark. What is showing? It is showing like the how they are arranged in this. After that, we make in a component, like large component, like any device or anything else. Now, if I talk about the atomic structure, like there are the different atoms, and their bond decide the its property. You know that, like there are the having the different atoms. There are the different kind of the atomic structure or atomic bonding. How they can found to each other. There are generally four types of and atomic bonding: ionic bonding, covalent, metallic, van der Waal. When we talk about the ionic bonding, ionic bonding is like when you give like I will talk about the, like NaCN. Na have the valency the +1, and the chlorine has the valency of the -1. So it has the tendency to give the one electron. It has the tendency to accept a one electron. If I talk about in terms of the electronegativity, I can also talk about the in terms of the electronegativity. Like the chlorine has the higher electronegativity than the Na. So it can accept a electron from this.
சுடுதண்ணி குடிந்தா இந்த சுடுதண்ணி குடி.
So ionic bond are generally formed by when the a electron is given by the another element. So that's why they have the like a positive charge and the negative charge. Which element gives the electron that has the positive charge, and which material, which element accept that electron that is a, have the negative charge. And due to having the charges, they have the electrostatic interaction, and they form the bond by using that interaction. In spite, when we talk about the covalent bond, covalent bond is generally formed when the two materials have the similar like valencies, similar electronegativities, or because when they have the same kind of electronegativity, or they are same materials. Like generally, there is example hydrogen. Element have the one electron in outermost shell, and similar like another hydrogen have the one electron in the outermost shell. So they want to be complete its outermost shell, they need two electron in that. So for that purpose, they share that electron. Like it has the one electron and is also the one electron. If they share to each other, both of them will have the two electron. So they will complete its outermost shell, and this kind of bonding is the called covalent bonding. And there will like here you can see they share the one electron, they can share the two electron and also the three electrons, or and they are called like and when we talk about the metallic bond, what is the metallic? It is generally found in the metals. How? Uh, when we talk about the metals, there are the generally they have the extra electron in the outermost shell. So what they have done, they they don't share that electron, or they also don't give to anyone else, any other element. But what they have done, the the extra electron in those element is generally float in their all the material. That's why it is called the sea of electron. So they can not bound to any element, but it can float everywhere. When we give to the charge to this metal piece, they will show its characteristics, like it can be flow in any direction according to the electric field. And when we talk about the van der Waal bonds and hydrogen bond, they are weak bonds compared to the ionic, covalent, and the metallic bond, because these bonds are generally physical bond. They are not involve the electron interaction. There is a no electron interaction, it does not share to each other. It is not to go on anywhere, or it is not formed any sea of electrons. So these electrons, what they have done, they in these bonds generally the uh, dipoles are formed. If I take the example of the argon, like argon have is spherical, but when it form the dipole, there is a like a negative charge and there is a positive charge to the end. Because if I talk about in the electron cloud type, so it is about the nucleus and it is the electron cloud. But when the nucleus shift to any side, if it, like just suppose nucleus is shifted here, then there is a like a partial positive charge and there is a partial negative charge. And in this kind, there is a dipole formed. And due to having this dipole in the material, they prepare a bonding. Like there is a partial negative charge, there is a partial positive charge, or they bound to each other electrostatistically. So this kind of bonding is very weak in the nature comparatively to the ionic bond, covalent bond, and the metallic bond. So here you can also see the, if I talk about the electronic interaction, so there is a strong interaction which are we talk about the earlier ionic bond, covalent bond, and the metallic bond are the very strong interaction. And we talk about the weak interaction. Weak interaction generally hydrogen bond and the van der Waal bonds. Generally, hydrogen bond found where the hydrogen is involved. You can also get that insight from the name hydrogen bond. And there is a van der Waal. It can be anywhere, found anywhere. So if I talk about the like properties, how the properties are get changed when we see there is a different kind of bonding. If I talk about the covalent bond, they have the high melting point due to the strong interaction between the elements. As they have shared the electrons, so they bound to each other very strongly. That's why they have the high melting point, because high melting point means they need the high energy to get in the liquid state. They are very hard in nature. If they are very hard, it means ductility is very poor. And their electrical conductivity is low. Just example is a diamond, graphite, germanium, silicon. They have the electrical conductivity low, not zero. It's not a very poor. There is a silicon and the germanium, which are counting the semiconductors. And graphite is also okay conductor, electrical conductor in terms of. When we talk about the ionic bond has a very high melting point due to they have the electrostatic interaction in between them. And their ductility is poor, and they have the very hard melt, very hard material. and their electrical conductivity is also low. And there is example like NaCl, zinc sulfide, and the cesium chloride. And we talk about the metallic. Melting point of the metal is vary according to the like which uh, on their atom, because they all have the same kind of bonding, but according to the atom size, it is vary, and how much electron they have in the outermost shell to donate to the system, like to form the sea of electrons. That's why their melting point is also varied. And when we talk about the ductility, generally they have the very good ductility, and it means they are poor, they have the very poor hardness, and their electrical conductivity is very high due to having the that electron sea. And example is like uh, Fe, iron, copper, silver, and there are the every metal has the kind of has a metallic bond. When we talk about the van der Waals bond, their melting point is low. They are very soft material, and their ductility is also poor, and their electrical conductivity is quite low, like just noble gases like neon, argon, krypton. And when we talk about the hydrogen bond, their melting point is also low, and they are very soft in nature, and their electrical conductivity is very low generally. And the example is ice. So if I see the atomic structure, what is the element that material have, and what kind of bonding those materials have, plays a crucial role in determination of the properties of that material. So if I see when we talk about prepare any ML models, then we see what kind of atoms that material have and what crystal structure it is going to have. So now let's start with the crystal structure. Uh, Crystal structure is uh, every material. Crystal structure generally is the showing every material have the in a regular pattern in the material. Like if I say you can see this cubical structure like an atom sit here, sit here, sitting here. So it is sitting in the infinite direction in the same pattern. Like it is a have a regular pattern in all the direction. Like if in the direction these have the different pattern, so it will be carried out in the infinite length. It will not change. That is called the crystal. And this structure is called the crystal structure. Then we will talk about the when we talk about the definition of the crystal structure, then we will also look for the unit cell. What is the unit cell? Unit cell is the a specific structure which is getted repeated. Like what is the smallest part of that crystal which is get repeated everywhere. Like when we talk about the any wall that is a make of a brick, and it is a if there is a uh, uniform kind of wall, that brick is repeated everywhere in a certain pattern if you see anywhere. So it's in the same kind, unit cell is the smallest structure which get repeated in the three dimension. And this pattern can be uh, move in the 3D in the millions times to form the like millimeter size or kind of crystal. As this crystal, this unit cell or the will have the a dimension of the atomic size, like the angstrom size. That's why it can be the million times or billion times in form a crystal which can be visualized by our eyes. Now let's talk about the different aspect of the crystal structure. Like if I give the proper definition of the unit cell? It is the smallest repeating unit of crystal. Okay. And when is repeated in the repeating unit of the crystal. And when it repeated in the different direction, it generate the entire crystal. So there are the some characteristics of the unit cell, like how you can say like differentiate between the different unit cell. So there are the some parameters which is generally called the lattice parameters. So like it is a, if I talk about this unit cell, like this is the x, y, and z, and this distance is called a, this is b, and this is c, and these are the called lattice parameter. So lattice parameters a, b, c, yani कि, it means different edges of the this cube. This is a unit cell. Always it is not a cube, and there are the some different parameters also, like these angles between b and c, that is called alpha, between b and a, that is gamma, and between a and c, that is a beta. So these are the angles alpha, beta, and gamma. And by using these six lattice parameters, alpha, beta, gamma, and A, B, C, you can get the all the insights of the unit cell, how it is a big. And generally, the unit cell and the crystal structure is characterized by using these lattice parameters. When we talk about the like unit cell, there are the a terminology which is generally used: primitive unit cell and the non-primitive unit cell. What is a primitive unit cell? Primitive unit cells generally have one atom per unit cell. What does that mean? Like I show you in the 2 dimension, just not on the 3 dimension. Okay, like these are the atoms in the 2D plane. So if I talk about the primitive unit cell have the effective elements, one effective element per unit cell. Like if I talk about this unit cell, then it has the one. How? If I talk about this element, this is shared by the four, this kind of unit cell. So effective atom at this corner is 1/4. Similar, this is the 1/4, this is 1/4, and this is also the 1/4. So effective atom at this place is the 1. So if I take another example of the unit cell here, if I choose this kind of unit cell, this is also the uh, primitive. Why? Because when it is sharing, the effective element is here also 1. But when we talk about the non-primitive unit cell, it is not 1. It would be the larger than the 1. Then that kind of unit cell is called non-primitive unit cell. Now we talk about the different kind of unit cell. There are the generally 4 types of unit cell. First is primitive unit cell. Second is body centered. Third is face centered. And one is the base centered. When we talk about the when we talk about the simple cubic structure, then this kind of this unit cell are found. But when we talk about the other structures like orthorhombohedral, orthorhombic, tetrahedral, then there there are different these 4 type of structure are found. There is also involved the base centered one. So what is the primitive? Primitive one have the atom at the only at the corner of the cube or the structure. Like they have the atoms here, here, here at the corners only. That is called the primitive, and it is denoted by the P. But when we talk about the body centered have the atoms at the corner also, but this corner also, this uh, crystal structure have the one atom at the body center of this cube. Like this is the body center. Sorry. But when we talk about the face center, and this is generally represented by sorry. Let's talk about the face center. Face centered structure have the atoms at the corner as well as the face center of the this structure. Like if you see this is the face, so it has the one atom at the face, one atom at the this face, one atom at this face, one atom at this face, and one atom at this the front face. So in such a way they are formed. And what is the base centered? Base centered is a kind type of the face centered cubic structure, but they have atom at the corner as every other structure have, but they have the atom at one opposite face, only one opposite face. Like sorry, face centered have in all the three faces, but it has the only one opposite face, not all the threes, and it is called the base centered crystal structure. And this is a body centered, base centered, and the or sometimes it is called also the end centered. So it does not make you the confusion. And they have the like if I see here, this corner has shared the 1/8 electron, because at this corner you can see there will be the 8 unit cell for here and the for upper side. So there are the total 8 cell which are shared this atom. So effectiveness of this atom is for a unit cell is the 1/8. Similar, this all other atoms also have the 1/8. So the total number of atoms here, like there are the 8 corner, and every corner has the effective atom number is 1/8. So there is a total 1 atom per unit cell. When we talk about the BCC, there is also have the 1 atom at the corner as a primitive one have. Yeah, it means 8 into 1/8 plus there is a 1 atom at the body center which is not shared by any other cell. So this is complete here. So there is a 1 and 1 plus 1 2. So body centered body centered structure have the 2 effective atoms. And when we talk about the FCC, here every corner have the 1/8 plus, but here you can see there are the fixed faces, but the atom which is sit on the face, it is shared by the 2, because there is a unit cell here also which will share this atom. So the effectiveness for a cell is half. So it is a 1 or it is a 3. So there is a total 4. And if I talk about this will be the 1/8 into 8 plus there is a one only 2 faces which have the atom on them. So there will be 1 plus 1, 2 effective atom for this. Besides this, there are the 7 types of crystal structure, and they have the different Bravais lattices. So there will be the 7 type of crystal structure like cubic, tetragonal, and having this which have the different arrangement of the alpha, beta, gamma, and ABC. Maybe all of you are the familiar for those. Like just for example, cubic has the A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, and it will have the all angle would be the 90°. If I talk about the tetragonal, then there is a is equal to b, but it is not equal to c. It means the c is can be equal or not be equal to the a, but all the angle alpha, beta, and gamma would be 90 degree. And we talk about the orthorhombic. Alpha a is not equal to b is not equal to c. It means a, b, and c, all the three edges can be different, but alpha, beta, gamma are also 90 degree here. But when I talk about the monoclinic, monoclinic have the different, can be have the different sides, is not equal to b is not equal to c, but here alpha and gamma are equal to the 90, but it is not compulsory for the beta, it is also should be the 90. It can be 90, but it cannot be 90 here. And when I talk about the triclinic, uh, a is not equal to b is not equal to c, and alpha is not equal to beta is not equal to gamma. So they can be equal or they cannot be equal to the 90 degree. When I talk about the hexagonal has the a is equal to b is not equal to c, but alpha is equal to beta, they both are 90, but gamma should be the 120 degree. And when I talk about the rhombohedral, or sometimes it is called the trigonal, they have the same kind of a is equal to b is equal to c, but alpha is equal to beta is equal to gamma, but alpha and beta are equal to the 90 degree, but gamma is not equal to the 90 degree. It can be the different angle. So these they have the seven type of crystal structure, and the different type of crystal structure can be in the different form, like simple, it can be the simple, and it can be the like a body centered, it can be the base centered, and not every structure have the all four. Some have the only one, some have the only two, and according to that they totally count in the 14. So we will focus on the cubic. uh, Cubic structure only have the primitive, it means simple cubic. It has the body centered also, and it has have the face centered, and there are the some special kind of structure that is called the diamond cubic structure. Diamond cubic structure is not different, but it is a special form of the FCC. That's why it is not a count in the different kind of structure, because diamond is not a unique structure. Actually, it is like a different case of the FCC. So now after this, we will talk about the microstructure. What is a microstructure? Microstructure have the like as we show here, when you have a same kind of structure material, like but it get displaced, like just for example I show you for example of a wall. Okay, like you have a this wall. Okay, and there are the bricks are arranged in this way. Okay, and sorry, So for a nice pattern, it should be like this, and it get repeated everywhere. Okay, but when this kind of structure material have, that is called the single crystal. It means it follows same pattern everywhere. But just suppose a material, sorry, it has a different structure here, different structure here, different structure here, different here, and it get in the different part. Like here you got the this kind of a structure. Here you find it is in this kind. Here you find uh, another arrangement. Like if I told about the brick structure, it is like have the same structure of the brick, like of a wall, but at the edges they got different structure. That's why if I talk about this region, this as a single crystal kind of structure, it has the same pattern everywhere. Like it has the same kind of structure here. In this region, these are the same kind of structure, the same kind of structure, same arrangement, same arrangement, same arrangement. But at the boundary, they change their orientation. If you see, they have the same structure, but the orientation is a different. And that's why this those material which have in a large material, this is that region which have the same orientation, that is called grain. This is called grain. This is called grain. And the boundary which separate the different orientation, that is called grain boundary. So when you find every where material, that is generally polycrystalline. If you found like any metal, any steel, so generally in the practical application you will find a uh, polycrystalline material, not a single crystalline. That's why it is a uh, very important thing to understand the grain and the grain boundaries and the properties of the material. Like in the previous I discussed the property of the material, discuss the arrangement of these materials, these elements. But if this structure is the same, but it is also depend on the this microstructure. What is the grain size of the material? How the grain boundaries are formed? The every grain, how much boundaries it is? Why it is it is shared? How many a grain is shared? The has a shared the boundary with another grains, like this kind of, like it has the two boundary here, three, and this is the four, and maybe in below that there will be the another boundary. So that's why these things decide the properties of that material. And this grain processing, grain boundaries, which can be tuned by using the processing, different kind of processing. So yeah, we can see the large feature composed of the either nanostructure material or the periodic arrangement of the atoms, known as the crystal. As we know, the it has the everywhere the same structure, that is called crystal. As here, our feature are visible with the high magnification. If I see the the grain, if you have a copper piece and you can polish that, and you can see the different feature in the light microscope, that is the grain. And there will be, you can see the grain inclusions and the other micro features that make up the material. If you see the carbon, then you will sorry, like the steel, there will you find this kind of pattern of the carbides. This one, and it has a different structure. And if you see, this is the pure iron, and this is the mixed with the 0.88% of the carbon, and this is changed. And if you find the this structure have the high strength comparative to the pure iron. Why? Because it has the like carbon in between, and this carbide structure have the higher strength compared to the this material. That's why this is a kind of a composite, as we earlier discussed. Like here, Fe is mixed with the 0.88% of the carbon, and it make it more stronger than the pure iron. So these are features are the traditionally altered by the to improve the metal performance. So we can alter the grain size, grain boundaries by using the different kind of processing, or we can say it will tune the properties of the material. Now, let's take the 5 minute break. And if you have any query, please post that in the uh, chat box. I will look for them, and then we will start in the 5 minute round. Okay. Okay, let's start the meeting. Okay. Uh, the last topic about uh, this meeting will be the type of the imperfections. Like we have talked about the atomic orientation of the material, like how they can bound to each other, and then we will talk about. Then we have talked about the like what is the crystal structure, how they bound to each other, and there are different kind of crystal structure that have formed, and due to their crystal structure they have the different kind of properties. And after that we will see like there is a microstructure of the material is a like it is a the main thing which decide the properties of the material. Besides that, there is a thing which is generally is the type of imperfection. Like having the this kind of like perfect crystal structure, there is a not. So in a crystal structure, there will be the kind of defect will be there, like one point defect. Like there will be like a point defect is generally represent the when an atom is displaced, it is got removed from the material, and this kind of defects are called the point defect. And there is a type there is another type of the defect is the line defect. What is a line defect? A line defect is not a different thing. It is a like a series of the point defect, like it is a kind of a series of a uh, point defect. They are arranged in a line, and it is a like a one day defect. And there is another type of defect that is called the grain boundaries, or there will be the twinning, and those are the called the planar defect. These are the 2D in the nature. This defect has the 2D in nature. And when we talk about the point defect, as I told, point defect is a like is a uh, the kind of a 0D defect, and it is generally the vacancy or the interstitial. Like there is a different kind different atoms in the structure, and a atom got displaced, like it is a vacant this that site, that is called the vacancy, and it is make a distortion here, and it created defect here, so that is called the vacancy. And just suppose an extra atom sit in the structure, then it is called the interstitial, self interstitial. Agar if this atom is have the same material, like this atom comes like just suppose this is the copper, just suppose copper atom vacant its site, then it is called vacancy. But just suppose an extra copper sit here, just that just yes, you can see here this copper atom sit here, extra copper atom, then it is called the self interstitial. Or what is the interstitial? These sites which is not uh, cannot be occupied, and by the default crystal structure, that is called the interstitial site, that can't be occupied by the elements. But when this kind of sites is occupied, when the any alien atom, like the different atom or the same atom, then is called the interstitial impurity. And here the same element is filled, then it is called the self interstitial. And according to this kind of like vacancies and the interstitial, there are the we can see there is a two type of defect. One is called the uh, Schottky defect, and one will be the Frankel defect. What is the Schottky defect? If I talk about in the like in the metal case, when there is a only one type of element, just the last slide. So then it replace from its side and it vacant that, then it's called the vacancy. But if suppose like it has a two type of material, like one is the anion and one is the cation. In those cases, anion and anion and the cation both vacant this side. It means like or we can see the ion pair vacancy. So when to why anion and cation both vacant their side, because there should be the charge neutrality condition of the material should be fulfilled. Like if just suppose like anion cation is anion is moved, then it will leave the cation and it will have the charge. In similar way, vice versa will be there. So if there will be any anion or cation will be removed, so it is should be must, then the other one is also should be removed, and that is called the ion pair vacancy, because they removed in the pair. And when there is a uh, vacancies, then those kind of defect is called Schottky defects, Schottky point defects. And just suppose any other element like at the interstitial site there will become the atom, then it is called the Frankel defect. In the same kind of when the like in the case of the metal which have the same kind of element, then it is called the, then it is like one same element is replaced come here. But in the in the like a case of when it has the ion pair, like ionic materials, so there will be like these come in at the interstitial side from this side to here. So this kind of defect is called the Schottky defect, and these are the in the point defect in the nature. So it is the 0D also. But why this defect is come here? So when we talk about the gives free energy of the material, G is equal to H minus Ts, and this is the entropy. So for a stable thermodynamically stable material, G should be negative, and it should be the much negative to get a stable thermo to get its thermodynamically stable material. So for that purpose, if these atoms got vacant or there will be some kind of distortion happen in the material by using the point defect, so there is a chance of increasing the entropy. But when as the entropy is increased, what type of entropy will be increased here? Like that will be increased the configuration entropy. So the increasing in the this entropy, it will lead to the lower the gives free energy, which will make it more stable. And that's why it is found in every kind of material generally, because not any material is the perfect. If you can find it's a single crystal also, there will be the some defect will be present. So the vacancies of the material can be found by using this equation. And here QV is the activation energy for the uh, uh, activation energy for the vacancy. So this is the graph as we increase the temperature, how the vacancy will be increased. And from this graph, you are able to find the activation energy the for defect on defects. So it's which I uh, talk about. But like there will be the same kind of material can be replaced, and there will be the some other type of material can be replaced. So there will be the two type of point defect interstitial. So there will be like the interstitial or there will be the substitutional. What is the interstitial? Like the just suppose karo carbon atom comes here and sit in the Fe. So it will be sit in the region where no atom will be present. But if that have the same size of this material, this element, then it would be replace this atom here, just as like copper in the nickel. That replace the nickel atom at the place and replaced by the copper. Then there is a another type of defect that is called the line defect. What is the line defect? Line defect is, as I told earlier, line defect is a just a series of uh, not add here. Okay, you can see here. It is a, like a series of point defect. Like here you can see these uh, row have the like okay, okay, like your crystal structure head should be the like the same distance everywhere. But at a point you find there is a like the row of element is break. Like here you can see, huh, here you can see this row is not get completed here, and it is like in between it break. So if I told about you like how it can be completed, like just suppose this element get bound this, and this will be bound to this will bound to this, and it will float this dislocation into the outer side of the material, as you can see here. So this is just a point defect which is formed in a line here. And there are the generally two type of the line defect. First is edge dislocation, and there is another one is the screw dislocation. What is the edge dislocation? As this is the example of the edge dislocation, because here you can see and see this pointer, and you can see this location will be moved in this direction. Why? Because this got bound to these atoms, and then it will be this bound to this, then it will bound to this, and in same way there is a dislocation move to the right as a to the right to the right side of the screen, or the left side of the my hand. But when we talk about the screw dislocation, what is the screw dislocation? Screw dislocation is a kind of like when it is get displaced. Like here you can see it is a get displaced. Like you have a you can see this by the example of a book kind of. Like I have a notebook, but when I stretch to this notebook, and it is get paper got moved one side, this to the this side, and these lines are not get aligned as they were earlier. So in this kind of and in same way here you can see this upper side is get displaced relative to the lower side, and at this point they got some kind of defects here. They got aligned here, but not aligned here. And here you can find there is a kind of a screw type of defect. That's why it is called the screw dislocation. And this both defect are in the line defect, and that's why it is called a 1D defect also. And here is the electron micrograph. Here we can see these dislocations. And now come to the like here also you can see the some example of the dislocation, like this tensile test. Here you can see when you uh, give the strain to the metal piece, it get some kind of a dislocation, and it get break. Now come when we come over the planar defect. Planar defect generally is a 2D defect. There is a generally two example of the planar defect. One is the twin plane. What is the twin plane? Like here you can see this structure and this structure have like a mirror image kind of. But when there is a kind they got a twinned any in a certain region, then just for example, I show you here. Mm, okay, just suppose mm, let's- just suppose you have this crystal structure. Okay, now just suppose this have the same, but in between uh, it is a move just one unit cell upside. Then for example, it moved here, it moved here, it moved here, and you get this displacement in a such a way you find there is a mirror image of one. I'm not, I think I don't use it. Here you can see here. This is a twin plane, and here you can see there is a mirror image like this and this, and and when this kind of and you can see this atom is displaced from here to here to make this twin, but it is happening in the same grain. Yeah, it means in the same single crystal. So that's kind of thing is called a twin plane, and it is formed in a plane. That's why it is called a 2D defect. And here is some example, like you can see there is a one grain, but there is a different kind of structure in the between that which is formed in a in this direction. That is called the twin boundaries. And there is a another thing is a grain boundary, which is also the called planar defect. Like there is a grain boundaries, grain are the 3D uh, 3D thing. So when they touch to each other, they will form a boundary. That's called a grain boundary. But when 3D things get touched to each other, that will form a 2D plane. So that boundary is a planar boundary. And as we know about the grain boundary, which we here, discussed here. So here they have the orientation this, but here they have the orientation this. So at this kind, at this boundary, they have the defect form defect, because they all these things have the different kind of structure. So there are in this boundary, their atom get oriented some other kind of other thing. So they are not uniform. For example, I have to go for the PPT, I think. If I go here, this one. So at the boundary, they are not like in the same arrangement as they are in the grain. So this is a kind of a defect thing. So that's why this is also called the 2D defect. Or I think I have discussed all the things which are taught in the second week, and in the first for the first week we have discussed some case studies which in the last class for how the ML can be work in the material science. So now uh, we can discuss about some questions. Please write your question in the chat box so I can go for those. Is there any question? Hello, am I audible? Hello, Nikhil. You can unmute yourself and ask your question.
Yeah, hi, sure. There is a graph used in Gibbs energy, right?
1 minute, 1 minute, 1 minute. Actually, the sound is ah.
Okay.
What's in my PPT or in the there
Yeah,
is a
in your PPT only.
in the search PPT.
No, no, yours PPT.
Uh, 1 minute. कहाँ गया भाई? Oh, got it. Here it is. This one.
Yeah, yeah. Can you explain it once?
Sure. Ah,
Okay.
1 minute. Actually, your sound is too much high. So you are want to explain me this graph. So if you see the equation, that is the uh, NV is equal to N exponential minus QV over KT. Okay. But when I uh, write N here, NV over N is equal to exponential minus QV over KT. So if I plot between the NV over N and between the T, because these two are the variable, because QV is the fixed for the K is also the constant, and when I plot between the NV over N or and temperature, then I will get this kind of exponential plot, like the exponentially increasing. Okay, so that's why this plot is this kind of plot, like the exponential plot. So besides this, we can also plot between the NV and T also, because there is a no need of the like NV over N, because N is the vacancies at any certain temperature, like at the room temperature, which is like a kind of a constant. And same as if you take a log between those, like if I take a log NV over N, then log of exponential becomes like minus QV over KT. So if I plot between,
Yeah.
it is a plot like y is equal to mx plus c, kind of. Okay, where m is the q over k minus q over k and x is the 1 over t. Y is equal to log nv over n and m is equal to minus q over k and x is equal to 1 over t. If I plot between y and x, then I will get the slope of that plot, and from that I will calculate the QV. It means the activation energy for the vacancies. Maybe you got the explanation what you want.
Yeah, sure, I got it. Thank you.
Any any other question? In the search note, if you want to ask anything, you can also ask those things also. No other question. Okay. Okay. And you have any like anything else what we can discuss in the next session, so you can will be the familiar about the like how machine learning and artificial intelligence can be useful for this course, like uh, uh, hello Ishwar, I have shared the last PPT also on the portal, and this will be also will be the share to you, to everyone straight, this video and this PPT. Any suggestion from your end, like No, I want to ask about like you will be learn about the ML things also, because I feel like there is a I have the much time than the content. Okay, let's end this session. If you have any query, you can post uh, on the YouTube comment also, which will the link of this the YouTube link of this session will be shared to all of you. So please comment if you have any query, or you can also post your comment in the question answer session, question answer section at the NPTEL portal also. I will see there all of your question. Okay, in the next session. So let us meet at the next session. Thank you so much. Uh, Hello, Sumita. You can find the first week material on the NPTEL portal. There is a section there for about the live interactive session. You will find any Google sheet there, and that have the all the slides of the as a I have will take the interactive session. You will find its YouTube link as well as the PPT of that live interactive session. If you have any query about any live interactive session or the content of the uh, like any other content, you can ask. Any other thing?
Hello. Thank you, everyone. Let's end this session. Meet you all into the next session, next Sunday. Thanks.